So I want us to take the derivative of this function here, g of x. So we're going to do this using the definition of the derivative. So if you recall, we take g prime of x, that's going to be the limit as h goes to 0 of g of x plus h minus g of x. All of this is going to be divided by h. Okay, let me fix this x so it's a little more clear. Okay, so we're going to go ahead and plug into this formula using this the function that we've been given, the expression for the function that we've been given. And we can, the limit hasn't done anything yet, so it's just hanging out. You got to remember to keep writing this every time, just to make sure we don't lose it. And then we're just going to plug into this. So remember, g of x plus h, if g of x is 2 over x, then this is 2 over x plus h. We're just taking this formula and wherever we see an x, plugging in x plus h. And we subtract from that g of x, which is just 2 over x. Okay? Now we're going to take all of this and we're going to divide by h. And now this is one of the trickier ones because the arithmetic, the algebra, the manipulations you have to do here are all, is maybe not the most straightforward thing. So when we see this, we see a difference of fractions. So we should, here in the numerator of the big fraction, we see a difference of these smaller fractions. So we need to combine these fractions together, which means we need a common denominator, right? Right now we have an x plus h on the left and an x in the denominator on the right. So we need a common denominator. And we're just going to do that. I'm going to kind of breeze through this, but you might need to review, your adding fractions when you have these kind of x plus, these expressions with x's and stuff. But basically the common denominator is going to be their product here. So I get 2x over x plus h, or x times x plus h, minus 2 times x plus h divided by x times x plus h. So you can see what I did to get from this numerator to this numerator. And we still have this whole over h kind of going on here. Okay, I'm just going to scroll up here a little bit. So now we have this here, and we can actually combine some of these, the numerator, we can simplify a little bit. And again, this limit is still hanging out. We haven't evaluated this limit yet. So we're still just hanging out. H is going to go to 0 eventually, but it hasn't yet. So now we're going to take this 2 over x times x plus h minus 2 times x plus h over 2, or x times x plus h. We're going to combine those and we get 2x minus 2 times x plus h. And I'm actually going to do two things here. One, I'm combining this to one fraction, so that's 2x minus 2 times x plus h, all divided by x times x plus h. This is my numerator, but instead of dividing this whole thing by 0, I think it would get confusing to have a fraction over a number, a fraction in a fraction. So instead of dividing by h, I'm just going to rewrite that as multiplying by 1 over h. Right? This is just to keep my work a little more organized here. Okay. Now what can I do with this answer here? Well, I can start distributing and manipulating the numerator here. So the limit as h goes to 0, just hanging out. 2x minus 2x minus 2h over x times x plus h times 1 over h. Cool. So now the question is, what do I do with this? Okay, well, you can see the 2x minus 2x, these are canceling. So we can see that these are starting to cancel. So we can go ahead and simplify this, and we get the limit as h goes to 0 of negative 2h over x times x plus h times 1 over h. And now we can see that we have some simplification happening here. We have some cross multiplication, or sorry, some cross canceling happening in the multiplication here. Basically, this h cancels with this h in the denominator. And so we can simplify this to just the limit as h goes to 0 of negative 2 over x times x plus h. And now this limit as h goes to 0 has been patiently waiting this whole time, so we can finally go ahead and evaluate this limit. In this case, we've gotten the h out of the denominator all alone, so we can just plug in h equals 0. So we can just plug in h equals 0, and we get negative 2 over x times x plus 0, which is just x. So this is negative 2 over x squared. Okay, cool. So this is our final answer here. This here, I can put it in the box, and this will be our final answer. And now, you might, I want to relate this to the original problem and see what happened here. So here in green, I'm going to relate this to the original problem. So the original problem, or the original function, I should say, is 2 over x, right? Now I can rewrite this as 2 times x to the negative 1, right? That's oftentimes how we like to rewrite these things. But the interesting thing here is that if I take that and I see, okay, what happened to this function? I took the derivative, right? All of this work here in yellow, I took the derivative, okay? And I got an answer out. And what did that answer look like? Well, it looked like negative 2 over x squared. But if I do the same trick that I did above, then I can simplify this, or I could rewrite this as, let's say, negative 2 times x to the negative 2, right? And so relating this original problem stated this way and the original problem stated this way, you might notice some patterns. And eventually, when we learn about the power rule, you're going to be able to formalize exactly what that pattern is. But for now, if you just get the work that I did here in yellow and you get this final answer, that's kind of what we're hoping for. Okay, cool. So there's another problem I wanted to do here related to derivatives. So you remember from lecture that I talked about the derivative in the relationship with rate of change and slopes of tangent lines. Okay, and particularly I want to focus in on the slope of tangent line. The instantaneous rate of change we talk about in 4.2. It's more of a conceptual idea, but the slope of the tangent line I want to talk about with this example here. So let's find the tangent line to the function f of x equals 3x squared plus 1 at the point x equals 1. I'm going to move this a little bit to give myself some space. Okay. So how do I go about doing this? Well, remember, we need to find an equation for a line. And to find the equation for a line, we need two things. So we need two things needed for the equation of a line. And what are they? They are a line. They are, one, you need slope, and two, you need a point on that line. Okay, so we're going to think about the properties of a tangent line for our function at a point, and use that to conceptually to figure out what we need to do to figure out what these 2 points are. So if you remember, conceptually, a tangent line just takes a curve, right? And you pick a point on that curve, and you get a line tangent to that curve at that point. So you get something like this. So conceptually, this is like what it looks like. But let's think about what we get. We get here a point on a graph and on the line. So this point is on the graph and it's on the line. And then the slope of this, remember conceptually the slope is the derivative. Slope is the derivative at that point. Okay? So let's go ahead and use this conceptual analysis to kind of figure out what the actual line needs to be. So let's start with the point, because the point is easier. We don't need calculus. So a point on a line, right? A point is an ordered pair. So 2 is a point. It's an ordered pair. We need an x and a y. The x is easy. We're given the x right here. X equals 1. But the y is a little is not as obvious. It doesn't just fall out from here. But it's not too bad. You can just use the fact that this point lies on this graph on the blue curve, meaning that I can just get the y coordinate by plugging into f of x. So this is f of 1. Now I need to actually figure out what f of 1 is, so I plug it into the original equation given up here. So f of 1 is 3 times 1 squared plus 1. So that's 3 times 1 plus 1, so this simplifies to 4. So I get the point here, 1 comma 4. Okay? This is my point on the line, and now I need a slope for this. Okay, so I need a slope. So to find the slope, right, I need to find f prime at 1. This is the slope of tangent line of the tangent line at x equals 1. Okay, so this is the slope of the tangent line at x equals 1. That's exactly conceptually what the derivative at a point does. That's what it means. It's the slope of the tangent line at that point. So now, the nice thing about this sort of problem is that we can give you this problem throughout the chapter. Once you learn more tricks for doing equations for more lines, right, or for more functions, you're going to be able to find tangent lines more easily, because now it's just a matter of, hey, can I take this derivative? Do I know how to take this derivative? As you learn more tricks, the answer to that question will become yes for more functions. Okay. But for now, the only trick that we know, or the only method we have for solving, finding derivatives, is using the definition of the derivative. So let's go ahead and do that here. I'm going to do that in green here. So I want to find f prime of 1. Remember, that's the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. Okay. So our answer here should be a number, right? Because we're plugging in a point. There should be we're taking the limit as h goes to 0. There are no x's here, so it's just, after all of this is said and done, we're just going to end up with a number. So let's go ahead and start evaluating this. So f of 1 plus h, remember what our formula was up here. So this is the limit as h goes to 0. Again, this limit is just going to hang out for a bit. We get 3 times 1 plus h squared plus 1 minus 3 times 1 squared plus 1. Okay? All of this divided by h. Okay? So now I can simplify this a little bit more. So the limit as h goes to 0 of, now this I can expand out here. So this is 3 times 1 squared plus 2h plus h squared plus 1. Right? That's what happens when I expanded this out. And over here this is minus 4. Okay? All I'm doing is some algebraic manipulations here. So if you, oops, what happened here? Sec. Let's have to go through all of this again. Okay. Okay, here we are. Sorry. So we end up here. We have the limit as h goes to 0 of this guy, right? And I'm just doing some algebraic manipulations here, and just trying to simplify it. My goal is to get the h's to cancel, okay? And so we're going to go ahead and distribute this through and start to cancel as much as we can. So we have the limit as h goes to 0. Then we distribute this 3 through, and we get 3 plus 6h plus 3h squared plus 1 minus 4. So 3 plus 1 minus 4 is 0. So that's nice. Let me try to get this straight. We have divided by h in the denominator. So again, like I said, 3 plus 1 minus 4, we're just combining like terms in the numerator. We're combining all of those constant terms, and we get 0. So we get 6h plus 3h squared over h. Okay? And now we can factor an h out of the numerator, and we get the limit as h goes to 0. And we get h times 6 plus 3h over h. And now that we're multiplying an h in the numerator and in the denominator, we can cancel these h's, and we get that this is the limit as h goes to 0 of 6 plus 3h. And finally, there's no more h's in the denominator, so we can just plug in h equals 0, and we get that the answer here is 6. Okay, now we pause and breathe because we've just done this limit that took quite a bit of time. But let's take a step back and remember why we took that limit, right? We're taking that limit because it's giving us the derivative at this point, which is the slope of the tangent line at that point. So now we have these two pieces of information. We have this this point here, okay, and we have this slope down here, right? So as a reminder, this is the point, and this is the slope, okay? And if you want the equation of the line, there are a few ways to go about it. You have a point and a slope, so you should probably use point-slope form, but there are other ways to do it, and maybe I'll talk about that as just a little reminder. So you can use point-slope form, which, if you remember, is y minus y1 is equal to m times x minus x1. M is the slope, and x1, y1 are the coordinates for your point. So since the point, if you remember, is 1, 4, then this is x1 and y1, okay? So if you plug that in, like I just said, you get y minus 4 is equal to the slope with 6 times x minus 1. Okay, and now we typically like to see equations of lines written in what we call slope-intercept form, which if you remember is y equals mx plus b. So we're just going to rearrange this equation until our line looks, our equation looks like that. So 6, I'm going to just start by distributing this 6x minus 6, add the 4 over, so y is equal to 6x minus 2. Okay, and this would be my final line. There's a way to get, there's also a way to do it without using point-slope form, but maybe I won't spend as much time on that. And yeah, so this is your final answer here, right? And now, this sort of problem we're going to continue to see throughout this chapter, like I mentioned. The only difference that's going to change is this middle step, where I took all of these steps to compute the derivative. In the future, you're going to have tricks for computing the derivative, and shortcuts for computing derivatives. And so you're going to, in this step, instead of using this limit definition, you're just going to use the shortcut to get your derivative, and then plug in your point and get the slope. And so once you have that, then you can use point-slope form or your favorite method for getting the equation for a line from the slope and the point. Okay. Thank you all, and have a good day.